Hello, once again, 7th graders, and welcome back to my YouTube channel. So we're going to continue our discussion today of these numbers that are existing in bases other than base 10. So for instance, we know that 29 is a prime number. Of course you do. It just has two factors, 1 and 29. But what about if we had 29 at base 11? Is that a prime number? The way we're going to go about answering this question is to consider what the place values of each of those digits is. That is, that 2 is in the 11's place, I should say. And then that 9 is in the 1's place. Okie dokie. Oops, I'm starting to write a 10 there. That's a mistake. There we go. And yeah, there we go. So as we can see, 2 times 11 to the first. So I've got 22 as that value, and this is a 9 in the 1's place. So we can answer this and say, yes, this is in fact a prime number. What about base 12? Let's see what that comes out to be. Let's see. So that's going to be a 2 in the 12's place, plus a 9, still in the 1's place. 12 to the 0th is 1. And so that's going to be 9, but wait a second, 2 times 12 to the first is 24, and 24 plus 9 is 33. Interesting, this is not prime. So, is 29 at base n always a prime number for any natural base that's above 9? Pretty clearly, the answer to this question is no. Okay, so moving on with our discussion here. Find a natural number, base n, such that 1 6 at base n is some prime, where obviously n has to be greater than 6. If my digit is 6, the smallest base can be a 7, right? So in that case, now I just gave up one of the possible correct answers here. In fact, take a look here. If we did 1 6 at base, let's try that, base 7. So what would that give me? 1 times 7 to the first plus, let's see, start to write this. I have 6 in the brain. No, actually, you know what? No, I think I'm going to write this. 6 times 7 to the 0th. There we go, like that. All right, so this is going to be a 1 in the 7's place, a 6 in the 1's place. Add these digits together, it's 13. Oh yes, I found a prime number there. I wonder if I tried something different. Maybe I just got lucky. Let's try 1 6 at base 11. That's another base bigger than 6. So that's going to be a 1 now sitting in the 11's place plus a 6 in the 1's place. Okay, so I have 11 plus 6, that's 17. Alrighty. I wonder if this is always going to be the case. Let's try one. I'll try one more prime number. Let's see, or investigation anyway. So 1 times 19 to the first plus 6 times 19 to the 0th. So this is going to be a 6 in the 1's place, a 1 in the 19, so that's 19. Wait a second, that's 25. This is not, so that's not prime. So, all right. So hopefully we can see here that, yeah, base 7 worked, 11 worked, 19 did not. Okay. What about this one? Try 3 2, base of n. Let's try it with something greater than 3, like a 5 sounds good. And that's going to be a 3 in the 5's place plus 2 in the 1's place. 3 times 5 is 15. That's a 17. So that works out. All right. If I did 3 2 at base 13, that's going to be a 3 in the 13's place plus a 2 in the 1's place. That's obviously 2. And that's 39. Interesting. So again, I'm able to show that, yes, this one too is also prime. Do you suppose that the base itself has to be prime? Well, I'll tell you right now, I'll spoil a little bit for you. In fact, it doesn't. Because consider that 3 2 at base 9, well, we see that 9 is not a prime number, okay? So where am I here? I've got a 3 times 9 to the first. That's a 3 in the 9's place, and a 2 in the 1's place again. Okay, so that's a 2 right there. And 3 times 9 is going to get us 27. And 27 plus 2 is 29. At which point you're starting to wonder, wait a second, is 3, 2 at any base? Whether prime or composite base, is that always going to be prime? No, I can find counterexamples. Consider 3, 2 at base of 6. That's a 3 in the 6's place. And a 2 in the 1's place. So that's a 2. 3 times 6 is 18. As you can see, that comes out to be 20. Okay. Now, let's move on. So we've explored that little bit of place value theory in these bases and how they relate to primes. Let's take a look here at exercise 81. Find exercise 81. And you can see n is going to be equal to a, b, c, and d, where these are going to be digits, right? It's not saying a times b times c times d. So let's get that out of the way. Because, yeah, I mean, a is in the thousands place, like so. B is in the hundreds place. C is in the tens place. D is in the ones place. So I can, in fact, split up these thousands here. You see this? I got that 1,000, 100, 10. Basically, I can split off a 1 from that 1,000. That's what I'm trying to say. 1 from the 100, 1 from the 10. Okay. So, with that, notice that we can write on these spaces here, we could just say, hey, let's see what happens here if I just kind of regroup this thing. That is to say, if I see I've got the 1s right here, a times 999 plus 1, b times 99 plus 1, c times 9 plus 1. So if I now factored out a 9 from this, that is to say, we can see where I'm going with this. Say 9 times the 111, like so. And, okay, I can show then that when I'm factoring this, wait a second, hold up. If I've got a times 999, couldn't I just call this 1 times, isn't this 1 times a, and that's b, and that's c? I should say that. Because indeed, when I've multiplied this out, that should be an a here. So let's leave those letters there, a, b. In fact, there's that c. And then this right here is going to be, well, yeah, it's going to be another c. Because, again, I'm factoring out the c. c times 9 times 1. So, oops, I drew that to the wrong space, didn't I? See, that's where I'm going to go. Like so. So now that I've got this, if I factor away a 9, this is where it gets confusing if it wasn't already. This 9 right here times a times 111 plus, you see I'm factoring, this 9, see I'm factoring this 9 and this 9. I'm factoring these all away. And I'm leaving behind what amounts to a, the b, and the c, and the d. So, since I can show the 9 divides that, 9 is a divisor of that factor, this is going to work, it's going to follow here, 9 divides n, if and only if 9 divides a plus b plus c plus d. So this is kind of an extension. It's a algebraic proof is what it is of how you can add up the digits on some number, and if that sum is divisible by 9, so is the actual number in question. Yeah, so that's where that comes from. So in that exercise 81 that you saw right there, yeah, that's all you have to do. You just do that. Now, exercise 82, it asks you to simply consider, a couple parts of this exercise. 1,120 equals 8 times something. 7,120 equals 8 times something. I'm going to let you do this on your own. I won't give this one away. Just sit, pause it for 4 minutes. Okay, so you're back. Good. Now, once you've completed that, let's go on to exercise 83. And that's right down below it there. There we go. So complete the following argument that for any n, it's an element of the set of whole numbers, 8 is a divisor of n if and only if 8 divides the number expressed by the rightmost 3 base 10 digits of n. So take some whole number, then by division theorem we may divide n by 1000 and get n equals 1000 times q plus r for elements of whole numbers q and r, such that r is less than 1000. Fill that in. It follows that r is the number expressed by the rightmost 3 base 10 digits of n. So now 8 divides 1000, and therefore 8 is the divisor of 1000 times q, because it won't matter what I multiply 1000 by if it's another another whole number. So if 8 divides n, then by exercise 48b we have that 8 is a divisor of r. Conversely, if 8 is a divisor of r, then by that previous exercise 48a, 8 is a divisor of 1000 times q plus r, which equals n. Okay? So there's that. All right. So that's your exercises for today. You should be up through exercise 83. Sorry for the long video, but I hope that it was worth your while today. And I will talk to you again tomorrow. Be good for your parents and have a great